Welcome back to ECE 442, 542. It seems like a year since we were here, but we'll try to make up for that lost time. This is a review session for exam number 1. I'm not really going to go over this exam number 1 process. It was just mentioned about an hour ago, but it's there in case you pull this up and need to find it. It's in 2 different places. The topics you should be able to find several different places. I've tried to consolidate the topics into a list of topics on D2L, but the material on homeworks 1 and 2, that's what you're responsible for. And it really does not include explicitly any material in lectures beyond the 3rd of February. Today's material is not really a part of exam number 1, but I think it helps you understand what you're doing with the Z-transform. Now, topics, just quickly, I've tried to sort of put those in between blue lines. Here is what I've called in the past our sort of square dance. It's a square, and you need to actually be able to dance around that square, meaning you need to be able to convert difference equations to block diagrams to state space, and those block diagrams are actually all delay block diagrams. And I'll make this available as far as the notes, so if you miss something, you can fill it in hopefully later, because I may want to quickly go through this list of topics and then start working or talking about some examples. Is that okay? So I'll quickly go through this. Block diagram, the all delay block diagram, how do we get a state space? What's the strategy? We need to define state variables, and how do we define state variables? Just outputs of the delay blocks. That's how we label our diagram, and then we can just basically generate the state space representation. Because the way I label my block diagram may be different from yours, but it's still okay. There's still valid state space representations. So I say a state space representation because it's not unique for a given system set of system dynamics. You also should be able to go from a state space representation in discrete time to a transfer function, and we'll derive that formula tonight, although it's basically consistent with what you've already seen for the continuous time case. It's just now we're doing the Z-transform and not the Laplace. And you can go either way. You should be able to go from difference equation to transfer function by Z-transforming, or cross-multiplying, realizing that z to the minus 1, z to the minus 2 corresponds to delays of 1 or 2 going from a transfer function back to the difference equation. That's why I'm saying you need to be able to dance your way around that diagram. Solutions to difference equations. And that really was sort of what we were talking about. Well, not quite, because we were starting in the transform domain in today's lecture. But if I give you a homogeneous equation with non-zero initial conditions, can you tell me what the result is, or what the solution is? What's y of n as a function of n? What's the closed form solution? If I give you a non-homogeneous, which means that I have a forcing function, some u of n that's maybe not just the unit step, maybe it's some exponential, maybe it's an exponentially decaying cosine, driving this difference equation, can you find the closed form solution for little y of n? And this is what we talked about today, actually, the structure. Maybe you don't explicitly solve for those partial fraction coefficients, but you know they are there, and so you just represent those as alphas or betas. You say alpha 1 times 1/4 to the n plus alpha 2 times 1/2 to the n, etc. Is that clear what I mean by structure? And I may go over an example of that also. I have a lot of examples. I don't know how much time I have. When I go horizontal, we're done, okay? I don't know if that made sense. But anyway, selection of the sample period or the sampling frequency. I could ask it either way. The sampling frequency could be written in or expressed in 2 units, radians per second or hertz, omega sub s or f sub s, and those are simply related by 2 pi. Omega sub s is 2 pi f sub s, or f sub s, and f sub s is the reciprocal or reciprocally related to the sampling period, the time interval in seconds between samples. That's capital T. We've agreed, for the most part, for this class, we want that sampling frequency to be 30 times the closed loop bandwidth. And maybe we'll get to an example of that also. Like I said, we may be here a while. We may get kicked out, I don't know. Janitorial staff comes in at 5 a.m., so we may get kicked down at 5 a.m. Everybody bring your pillow and blanket. You guys can take a snooze. I'll just keep going. Ha, that'll be the day. BIBO stability, bounded input, bounded output stability. What does that mean? That means if you have a system's transfer function, G of Z, then it's okay to not worry about things anti-causal and causal. Now you have a system. Now that system's poles need to be inside the unit circle. Equations of motion. Can you, if I give you something, a circuit and a mechanical subsystem, can you connect them all together to create some G of S or some set of differential equations? Like what you did for the first homework assignment. What was the first homework assignment? A DC motor, wasn't it? Z transform. If I give you a function of n, a waveform, can you compute the Z transform? Is that exponential? Is it constant? Is it an exponentially damped cosine, exponentially damped sine? Is it some linear combination of that? If I give you a difference equation and maybe drive that with a non-zero input waveform, now can you figure out what the Z transform of the output is? Or I might give it to you in a block diagram. That's why you have to be able to dance around that 4 locations in that earlier topic. Because I might give you this information in many different ways. You have to figure out what you need in order to get the answer that you desire or that's asked for. You may desire something that's not asked for. Well, give me that. If you can't answer the one I asked for, at least show me you can answer something. Hey, it might get you some points, right? If somebody's interviewing you and you don't quite understand what they're asking, ask them back and then say, you know what, I can talk to you about this. Well, that's what you're doing on the exam. Find the transfer function, either from a block diagram using block diagram algebra, Z transforming a difference equation, doing a state space, and this is what I said I will try to derive tonight. And this structurally looks like what the G of S did before. It's just now the S is replaced with a Z, and our system matrix is this Greek capital letter phi. Our input matrix is a gamma. The direct feed-through matrix is capital J. That's not the square root of -1. This is a matrix J, which is typically 0 if we don't have a direct connection between the input and the output. And H is our measurement matrix. This is an expression that you should just have in your head throughout the rest of the semester and know how to use it. And that's also helpful in that dance around those 4 locations in that diagram above. And this, I think, is one of the topics that I forgot to include on the earlier list of topics, is how do you find the settling time? And I could ask you for the 7.5% settling time instead of the 1% settling time, or the 2% settling time, or the 10%. Is that clear? Not that I necessarily will, but you know how to be much more liberal with the settling time computation, because it depends on this one formula. Unlike maybe in the analog or continuous time case where you were saying, oh, the 2% settling time corresponds roughly to 4 time constants. The 1% settling time corresponded to 5 time constants, although the textbook we used to use for this class was 4.6 time constants, because e to the minus 4.6 is almost 1%, whereas e to the minus 5 is a little bit less than 1%. Don't get too bent out of shape on that. Here I can be more, you can be more specific. Okay, that's the list of topics. Let's get started. And I could ask you one question. And if you miss the first part, I don't have to grade the rest of your exam, because it all hinges on that first question, the first part of the first question. All right, let's see if we can work, and I may work actually with one set of equations and derive a lot of different results from that. Let's find a state space representation and these could all be questions on the exam, given for the given difference equation. And let's say that the difference equation is y of n is equal to 1.4 y of n minus 1 minus 0.45 y of n minus 2 plus u of n minus 1 plus u of n minus 2. And I hope you already sort of have an idea how you could do this. But tonight I'm actually going to give you a different way of going from the difference equation to a block diagram. Maybe it will be more intuitive to you. It doesn't matter which one you use, just use one that you like. In that case, it's one you feel comfortable with. In this example, I'm not going to introduce some auxiliary variable w. That I did because I thought I could write it up on the homework more easily, and we'd already looked at something like that in class. Now let's try a different approach. I'm going to call this one construction approach, because you've already learned another one on, was it homework 2, where you had that new auxiliary variable. And the reason why we needed that was because we had delayed inputs, and we have delayed inputs here. In this particular approach, I'm going to assume that we can measure or have access to the output at time n and the input at time n. And that's a realistic assumption. This is fine. So we're going to assume y of n and u of n are available. Now what I'm going to do is just rewrite y of n in terms of y of n and u of n. And I'm going to describe what I'm trying to do. It's really just going to be a nesting of delays. And we've sort of done that. If you took a 340 from me or some other class from me that worked on this, you've seen this where we nested integrals in the time domain. Here we're nesting delays. And delays I'm just going to call d. That's an operator that's going to be a delay. If I needed y of n minus 1, if I operated on that by d, y of n, that would be y of n minus 1. Right? And if I need u of n minus 1, D operating on U of n gives me U of n minus 1. So if I apply D, the delay operator, to Y of n and U of n, then I'm going to have these two pieces on the right-hand side. I just have to scale the one by its coefficient. Maybe I messed up and I should have put some coefficients there, but it doesn't matter. But to be more generic, maybe I should have. What I now just said is if I delay 1.4 Y of n plus, need to make sure I'm getting the signs right, U of n, now I have effectively accounted for those two terms on the right-hand side. Are we okay with that? I wanted to create a Y of n minus 1 and a U of n minus 1. I can get those. I'm assuming I have access to U of n and Y of n. I just delay both of those and scale them by the amount that they need to be scaled. Now, I need to account for Y of n minus 2 and U of n minus 2. But that delay thing worked pretty well, didn't it? Well, now I'm effectively embedding, if I go down here and say, well, I haven't closed up this curly bracket. Let me now, inside that, delay something else. That's another bracket. Okay? Use your imagination. That's now a bracket. Okay? Square bracket, I don't know. I use it if I have about 6 different levels of brackets, but I kind of like that when it's different. Okay? So now if I have a delay and a delay that the next Y of n goes through, and if it's scaled by minus 0.45, I'm going to get this term accounted for. Oh, it's not minus 4.5. I may go more horizontal quicker than I thought. Minus 0.45. Is that what it was? And then I'm running out of space, or you might be on your paper, so I'm not closing anything up. Inside that weird looking bracket, I need to put another U to have a U delayed twice, so that I now have plus U of n. Now I'll close up that bracket, and I'll close up the other bracket. And now I'm saying that that right-hand side is equivalent to the beginning expression. Is that okay? And now, in my all delay block diagram, how many delays do I need? They're right here. I need 2 Ds, 2 delays. And Y of n is going to be the output of one of those delay blocks. So let me now put right here a delay block, and this is Y of n. And I have access to Y of n, and I also have access to U of n. And what do I have creating or coming out of that delay block? Well, I have the input to that delay block is in this curly brace. It's 1.4 Y of n. So I come here and I go, oh, I need to scale Y of n by 1.4. Now I'm kicking myself for not scaling these inputs. I now need a scaled U, but it's scaled by 1, so I'll artificially do that. Now I've accounted for this piece and this piece, and those will pop out of this delay block and give me Y of n, but I have in another term coming out of another delay block, don't I? And that's that weird symbol, but let me just call that signal. And that's coming out of another delay block. which is really right there. Meaning all of that D with these weird brackets is this signal right here. Then I'm delaying that, and now I know what's inside that weird bracket. It's made up of Y and U with some linear scaling on Y and U, meaning the input to this is now minus 0.45 Y of n plus U of n. And there's my new block diagram. It's an all delay block diagram that realizes that difference equation, and it does it differently than what you did maybe on your last homework assignment. I just wanted to give you a different way of creating a block diagram from a difference equation that has time delays in the input. Now, how do I get a state space representation from this? It's exactly the same process as before. Now we just assign our state variables and we assign those to be the outputs of our delay blocks. I'm going to make mine, let's say x1 of n right there and x sub 2 of n right there. And what's this point right here going into the rightmost delay block? That's x sub 1 of n plus 1, isn't it? And coming into the leftmost delay block, that input is x sub 2 of n plus 1. And now we have our difference equations. And we can write those in matrix form. We have x sub 1 of n plus 1 and x sub 2 of n plus 1 stacked on top, and that's our leftmost column of state variables, advanced by 1 unit of time. Then that needs to be some linear combination of our states at the present time in plus some scaled version of our input at the present time, U of n. And if we had multiple inputs, which I could have scattered around, we might have more than one column in that input matrix. And in the formula that I introduced earlier, this matrix, which I would call the system matrix, that's that phi matrix. This input matrix in the discrete time setting is the capital gamma. And now we just have to fill those in. How big is phi? What are the dimensions on phi? It has to be compatible with what's on the right and what it needs to generate. And that's 2 by 2. Phi always is square. So if you want to make me feel better when I'm grading, don't give me a non-square phi. Okay? You go, I don't know what phi is, but I know it has to be square, Dr. Tharp. That's correct. Okay? So now, what's the first row of phi for this particular problem? What's the 1, 1 entry? Now, we could make this really more complicated if I would have fed back y of n and there was this gain between y of n and x1 of n. That could complicate things, but I made it pretty easy here. But for now, y of n is simply the same as x1 of n, and that's directly feeding back. That's 1.4. That's making up that signal, isn't it? That star is x sub 1 of n plus 1. That's the output of that summing junction. We now need to create that or build that by all the arrows coming into that summing junction. We've now eliminated or accounted for the one coming up from below, 1.4 x1 of n. What's the next signal if we go clockwise around that summing junction? That's just 1 times x sub 2, isn't it? Now I'm really kicking myself for the choice of my coefficients on the u's. But what's the gain on the u? That's just 1. And that's this one, isn't it? It's blue. Didn't like Kermit. So I'll try to be consistent. Where's this one, the red one for the u? That's pretty difficult because there's only one more place for that to go, correct? That's driving x sub 2 of n plus 1 is u of n minus 0.45 x sub 1, and how much of x sub 2 do I have feeding back? 0. And what's my output equation? I only have one output, but I could make 3 or 4 outputs, couldn't I? That would just allow me to have more rows in my output matrix. I have one output. That means that I must only have one row in my output matrix, but I have to have how many columns? I have to have as many columns as I have state variables, which is 2. And to be, let's say, exhaustive, I can show that I do have a direct feed-through term. Is there a direct connection, or is u coming over here and summing to make y of n? It's not in this particular example. That's why this is a 0. And what's my H matrix? It only has to pick off x sub 1. And now in the notation that I had before, I think I called that H, and this was J. Questions on that state space representation? So we moved around that 4 square. We went from a difference equation to a block diagram to a state space representation. Question? Mm-hmm. So you're going to get different. So the question was, if you write this using the other technique that we talked about, which I think was applied on homework 2, your state space representation is going to look different. What's going to be the same is if you compute, now, your phi, gamma, h, and j may be different from mine. But if we both compute a capital G of z, we better get the same transfer function because it's supposed to be describing exactly the same system. Does that make sense? So you may not get the same, but you're going to get the same information. One of the things that we could ask about now is we could say, is that system stable? Here's another question. So that was question 1A. Here's question 1B. Is the system stable? So there's many ways of finding that, but now we have this phi matrix, which is a state space representation. If we find the eigenvalues of phi, those are the same, they will be the same as the poles of our transfer function, g of z. So you could z transform the difference equation, find your transfer function, that's capital G of z, and find what? The poles of capital G of z, and see if they are where? Inside the unit circle. If they all are inside the unit, if just one is outside, your system is unstable. Here, we'll do it a different way. Let's find the eigenvalues of phi, because we have that right now available to us. We could check the stability of the system by the eigenvalues of phi, the system matrix, and the eigenvalues are simply lambda I minus phi, the determinant of that, the values of lambda when this is equal to 0, those are the eigenvalues of phi. Now, if we do that for this particular problem, phi is square, I is a square matrix, it's 2 by 2. We now have lambda minus phi, and that was a minus 0.45. Then we had a minus 1 and a lambda minus nothing. That hopefully is lambda I minus phi. Your lambdas are on the diagonal, and you subtract the phi matrix, which could introduce a term in all 4 entries of that 2 by 2 matrix. We now have to just compute the determinant of a 2 by 2, which is the product of the diagonals minus the product of the off diagonals. Or it's now lambda times lambda minus 1.4 minus a minus 0.45. Is that okay if I just do that? That's now our determinant, or it's lambda squared minus 1.4 lambda plus 0.45. And if you have to go, please go. I don't want to keep you here if you have something else that you need to get to, okay? That's fine. It's recording, I hope, so you can watch it later. There is what we have, and we need to find the values lambda. Now, if you can't see this, plug it into the quadratic formula, but this is actually factorable as lambda minus 0.9 times the quantity lambda minus a half. So we have 2 roots, one at 0.9, that causes that to vanish, that polynomial, and lambda equal to 0 plus as positive 0.1 or 0.5, and that would be wrong if it was in the S domain, wouldn't it? That would be an unstable, but now all we have to do, we don't care. Actually, having positive values is probably a good thing for our discrete time setting, but it has to be inside the unit disk, and those are. So this system was stable. The roots are there, and both lambdas are less than 1 in magnitude, and if they were complex, which they could be, you take their modulus, or the absolute value of that complex number, make sure it's inside 1. If it is, then you're good as far as stability is concerned. Now, we could have checked stability the other way if we z-transform that difference equation. Whoops. Then we have 1.4 z to the minus 1 y of z minus 0.45 delayed twice plus z to the minus 1 u of z plus z to the minus 2 u of z. That's just the original difference equation, z-transform. We can now combine or collect our like y, coefficients of y, capital Y, and coefficients of z. We now have 1 minus 1.4 z to the minus 1 plus 0.45 z to the minus 2 equaling z to the minus 1 plus z to the minus 2 scaling u of z. And now we can simply compute y of z over u of z, which is now In the numerator, z to the minus 1 plus z to the minus 2, 1 minus 1.4 z to the minus 1. And maybe that's not easy to think about, so I would, if I'm finding poles and zeros, I would convert to positive powers of z. If I factor out a z to the minus 2 downstairs and a z to the minus 2 upstairs, those cancel, and I'm left with then z plus 1 upstairs, z squared minus 1.4z plus 0.45. And that denominator polynomial better look familiar. Now it's in terms of z instead of lambda, but it's the same polynomial, I hope. So the poles are now the roots of that denominator that factor's the same, and we're stable. So you could do that problem 2 different ways, 3 different ways, a lot of different ways. Yes?
If we did the eigenvalue way, how far should we go on the test? Can we do the calculator?
So the question was, how far do we go? You run all the way around the bases. But if you do it with your calculator, you need to tell me. This is from the calculator. So you could say, found the roots via the calculator. I would give me the polynomial and then say roots by calculator. Don't just say something and assume I know what you're doing. Okay? Yes? So why do we not have to worry about the region of convergence in this particular problem? The region of convergence, we were viewing that as waveforms. So now it's a little bit subtle, but now we're talking about a system. So if you go back and think about Laplace, 1 over s could mean 2 different things. It could be the Laplace transform of a unit step, or it could be an integrator as an operator. So that's sort of what we're doing here. We have a transform, capital G of z, that's representing a system. That system, we want it to be stable, which means if we hit it with bounded inputs, it better produce bounded outputs. That requires the poles of that system to be inside the unit disk. We didn't have to worry about a region of convergence. With waveforms, we do. There, that transform corresponds to a time domain signal, and we need to be told when that signal is active. Is it for non-negative ends? Is it for negative ends? Is it two-sided? Don't have to do that when we have a system. Is that okay? So when we have a system and I say, what's the stability? You're not so concerned with the region of convergence. That's really not an issue. Now we're talking about a system. Does that help answer that question? So it's a little bit on the subtle side, but we're talking about 2 different things to begin with. All right, now, let's say we had that state space representation and somebody says, I want the transfer function, but you forgot how to do it this way. We just did it, didn't we? And you go, you know what, I've got about a minute left on the exam. I can verify that I got the answer right. I'll just do it with the state space. Okay, so you're working your problem 2 different ways. Let's address this question. What is the transfer function of the given state space representation? And now we're going to derive the formula that I just gave you before. So this is now the discrete time. If you're texting this, SS to TF, right? State space to transfer function. And this is going to apply to any state space representation, not just the one we derive. So I'm going to say, let's say that our system is now x of n plus 1, and this x is now a vector. It's maybe 10 variables tall. X has 10 components. This is tall and thin as a state vector. It's then the system matrix phi times the state vector at time n. What's the dimension on phi if x, our state vector, is a 10 by 1 vector? Phi is square, isn't it? And it's 10 by 10. Gamma u of n. And if we had two inputs, what are the dimensions on gamma? If we have two inputs, gamma now, we know it has to have 10 rows, right? It has to be compatible with x when we form the product of gamma with u. But the gamma u product has to be compatible. And if u is two variables, it's a vector that's two tall, TWO tall, and one wide. It's 2 by 1. We now have a 2 by 1 entry for u of n, or a vector, scaling a gamma that's 10 rows tall and how wide? 2 columns wide. So gamma would be 10 by 2 if we had two inputs. In this class, a lot of times we just have one input, so gamma will probably be a single column. Is that clear? That's our dynamics. And then we have our output equation, which is y of n, no dynamics, h, x of n, plus j, u of n. Whoa. Now the beauty of this, in this formulation, is I don't really have to worry about the dimensions of y, u, and x. I can z-transform this generic equation. If I z-transform a vector x of n plus 1, what's that going to produce? It's going to be an advanced version of the z-transform of little x of n, isn't it? So that's z capital X of z. Is that clear where that came from? I'm just z-transforming little x of n plus 1. So that's an advance of 1, and z as an operator, if it was z to the minus 1, that's a delay. The reciprocal of that is z, which is an advance. So an x of n plus 1 is an advance of 1. That's a z times the z transform of little x of n. Phi was constant. The z transform of little x of n is capital X of z plus gamma capital U of z. Is that clear where that's coming from? And we can z-transform the output equation. Little y of n is capital Y of z, h, x of z plus j, u of z. And we're really trying to find a relationship between the transformed input, capital U of z, and the transformed output y of z, which means we have to get rid of or rewrite capital X of z, the z transform of the state vector, in terms of y or u. And that's given to us by the dynamic equation. It's just now we have to remember that z is a scalar, It's a complex number, but it needs to somehow be compatible with phi, which is a 10 by 10 matrix. Well, I can make that happen if I simply introduce a 10 by 10 identity matrix. I haven't changed anything. I've just made my ability to combine these two terms involving capital X possible. Now I can combine those, meaning from this equation, I can now say I have zi minus phi x of z equaling gamma u of z. And I can now solve for the z transform of my state vector, capital X of z, by hitting, and now these are matrices, so I have to be careful with my multiplications. They don't necessarily commute. I'm going to hit everything on the left by the inverse of zi minus phi. That then gets knocked away. And I have zi minus phi inverse gamma u of z. And that's what I wanted. I wanted x, capital X of z, in terms of u or y, so that I could get rid of or just have one equation that contained y and u. Yes?
Do we ever have to worry about the inverse not actually?
So now the question was, do we ever have to worry about that inverse not existing? The nice thing is, the short answer is no, because we have zi. Z is a variable, and I is an identity. So no matter what phi was, if phi was 0, we would still have that inverse existing, because z is a variable, and now we have z times the identity. That's a well-behaved matrix. It's a function of a variable, z, but that's okay. We can invert that matrix. We just have 1 over z's. If it's on the diagonal, that's an easy matrix to invert. But your calculators, the 89 and the Inspire, will do a symbolic inverse. If you give it zi minus phi, if z was a 4 by 4, I'm sorry, if zi was a 4 by 4 with z's on the diagonal, minus a 4 by 4 phi, it'll invert it. It'll get a little bit warm. It'll set their number crunch, but it'll work. Okay? All right, let's keep going. So now we have y of z equaling h times this x of z, which is now zi minus phi inverse gamma u of z, plus j u of z. And if we factor out the u of z, there's the formula that we were wanting to get before. And if we did that with our particular variables, h was 1, 0. zi minus phi, I have a z minus 1.4. My gamma was 1, 1, and my j was 0. Now I just have to symbolically invert a 2 by 2 matrix. But that's 1 over the determinant times the adjoint matrix, which is the cofactor matrix transposed. Yes?
Okay, John, do you want this to derive the formula? Or just
So on the exam, do I want you to derive the formula? The answer is no. I want you to understand and appreciate the formula and have it burned in your brain, or at least on your notes, and know how to use it and know why it's being used. But you don't need to rederive it. You've seen it derived, and hopefully it makes sense to you. So that was a valid question. But a lot of these things that we've derived, you don't have to rederive unless I tell you. Show me where that came from or derive this result. Does everybody remember how to invert a matrix? Do I need to do this? What? Calculator. Did it come up with the same? You should end up with the same result. You should end up with z plus 1 over z squared minus 1.4z plus 0.45. So the determinant of that is the diagonals multiplied together minus the product of the off diagonals, and that's exactly what this is. Then you do for a 2 by 2, you just interchange the diagonals and change the sign of the off diagonals, and that's your adjoint matrix. Multiplying that by a 1, 0, that gives you the top row, which is just z and a 1. And then you add those up by the input matrix, and that's the z plus 1 upstairs. Done. Okay? All right. So that's our transfer function. Now we might say another question. What is the 1% settling time for this system? Now, isn't this fun? I told you at 5 a.m. Still going. What's the 1% settling time for this system? Is it clear what I'm asking? If I gave you an initial condition for this system, how long would it take before, and you wouldn't be exciting the system, let's say, your u is 0, you now just have an initial condition, and you want to know when do I get to within 1% of where I started. So your initial condition might be selected so that y times 0 is 4.76. And now you want to get to 1% of that. 0.04, whatever I said, 76. Well, we did this before for a first order system, didn't we? So I'm kind of throwing you a little bit of a different problem. But don't despair. Don't be swearing. Oh, I said despair, not never mind. Z-plane. Where are your poles for this system? The eigenvalues were at 0.9 and 0.5, right? And that's where the poles were. Now, you have two eigenvalues, two poles. Those two poles are going at a different speed, aren't they? We have 1/2 squared, 1/2 cubed. That's what's its speed relative to 0.9? So I have 1/2 squared. That gives me 1/4, right? Or 0.25. What's 0.9 squared? 0.81. Which one is collapsing more rapidly? The one that's closer to the origin, isn't it? The one that's closest to the unit circle is collapsing the slowest. Because it's slow, it's dominating your response. Getting too much feedback, and this is a control class. Oh, I was probably standing under a speaker, wasn't I? All right. So, what I'm trying to say is this is the slow mode because it shrinks much more slowly, and it's all relative. But in this class, we'll just say concentrate on the slow mode, and this is the fast mode. So now I'm really looking at which of these has the biggest radius inside the unit circle. If you have a pole that's outside the unit circle, you're not going to have a settling time, are you? You have an unstable response, it's not going to settle. So don't worry about it. You just say, I have an unstable system. But here, you have a mode, you look for the one that's closest to the unit circle. That's the one we're going to, or the radius of that. This is that's the dominant pole or mode. That dominates your dynamics. That's what we're going to say. And because of that, that's the one value you can use in that formula. Remember our settling time formula. We're going to say that y of n, and this is now an approximate because you really have two poles and they both kind of play together. They're nice and they help each other. But we're just going to say, you know what, neglect the fast ones and just use the slow one and be done with it because we want something that's kind of seat of the pants, quick. We now say, okay, our big dominant pole has a radius of 0.9. That's our R. And so if we had a complex, we would find its magnitude. As long as it was inside the unit circle, we would use that biggest magnitude, and that would be our R value. Not the complex number, but the magnitude of that complex number. Is that clear? This is now raised to the n, y of 0. This is now our, let me say, the radius of slowest pole. And if they're complex, you're going to have a twin that's a conjugate of the one. So you're going to have two poles. We're just going to use the radius. That's how quickly they collapse, is by the radius. In our case, we now can say, oh, we want the 1%. So y of n is 0.01 y of 0. That's equal to 0.9 n y of 0. The y of 0, it really didn't matter where we started. As long as it was non-zero, we can divide it out. And now we simply use our logarithms or however else we want to try to solve this, but we can take probably the base 10 log is easier with 0.01, solve for n, and we have minus 2 over log base 10 of 0.9, and we end up with this equaling 43.7. So how many samples is it going to take before I get less than 1% of where I started? 44 samples. And that's our approximate 1% settling time. It's approximate because we threw away all of the other poles. We just looked at the dominant one, and we said 43.7. Well, we have to be discrete in the number of samples. Let's just pick 44. So we'll probably be within 1%, more than 1% of where we started. That's okay. Questions on that? Pardon? Yes? This is the settling time, 44 samples. Is that the... Oh, the time is going to depend on the sampling period, and I never even gave you that, did I? I just gave you a difference equation. So I never told you the actual time. This would correspond to 44 sample periods, whatever capital T happened to be. If capital T was 1 second, this would be 44 seconds. If capital T was half of a second, which is pretty long for a sampling period, that would be 22 seconds. Is that okay? I didn't tell you what T was, so I can't tell you what the true settling time would be. But if somebody gave you capital T, or if you'd computed that or used it, you would be able to calculate the real settling time, little, let's say, or capital T sub s. Is that clear what the question was, or what the issue was. I didn't give you a capital T, so I can't tell you. All I can say is it's 44 samples with the amount of information I provided. Is that okay? So now what if I said if, okay, this is problem, I don't know, F, 1F, 1G, I don't know how many parts we've had to problem 1. If U of n is 0.7 to the n cosine of pi over 8n for n greater than or equal to 0, what is the structure of y of n? Yes? We could. The question was, can we include a phase shift in that cosine? We can do whatever we want. I'm not going to right now because I hope, based on the solution to homework 2, you know that if somebody gives you a phase shift, that really just means you have a linear combination of cosines and sines that are exponentially damped with an amount 0.7. So when you see that phase shift, I would just say, oh, I have sines and cosines. And when I'm asking for the structure of y of n, even though I'm shaking this without a phase shift, that system is probably going to have some delay in it, so you're going to see not only a cosine but a sine, even if I start with no phase shift. Is that clear? Because it's probably going to be delayed by some amount relative to I'm just defining where I draw in the sand my time 0 by having a phase shift of 0. By saying I have a different phase shift, now I've just shifted my t equals 0 point or location. But you can convert this, if you have a phase shift, by trig, right? Cosine of a plus b. And then you get rid of that phase shift. You just have exponentially damped sine and exponentially damped cosine. And you can z-transform those. But now you can tell me what the structure of y of n is pretty quick, I hope. Meaning, I could say, what if the input u was nothing? We didn't have an input, and I said, what's the structure of y of n? What would you tell me y of n structure was? You see it? If now you have a non-zero initial condition, but no forcing function. What's the structure of y of n? It depends on your poles, doesn't it? Those poles give you the modes of your response. And where were our poles? 1/2 and 0.9. The structure of y of n without any forcing function, the way it's going to respond to an initial condition is going to depend on your poles. That's the natural way that that system wants to behave. And those poles are at 1/2 and 0.9. Meaning, I could have two different questions here. I could say, with u of n being this, that would be a forced or non-homogeneous difference equation. Or I could say unforced, that would be a homogeneous difference equation, and u of n would be 0. Is that clear? Let's look at both. So if I have a homogeneous structure, that's maybe a poor choice of words, but I hope you know what I mean. The structure due to a homogeneous difference equation is what I'm meaning by that. This is really the natural behavior of the system. That means if you just walked up to the system and kicked it, you gave that system a pulse, and it shakes, right? You basically have initialized the initial conditions, and it just now shakes. And since it's stable, it's going to be a well-behaved response. That would be the pulse response. in a discrete system. It's the impulse response for a continuous time system. You hit it with an impulse, that just energizes all of your energy storage elements, and then you just watch them decay. That's what we're doing here, except in discrete time. The structure for this, for the natural behavior, I'll just say y sub h of n, is influenced entirely by where the poles are. So it's now, if I just ask for the structure, I'm not asking for the exact value for y. This is now some linear multiple of one mode plus a linear multiple of the other mode. And let's just say that we were looking after n equals 0. We have to kick it sometime. Let's just agree that we kicked it at 0. That's the homogeneous structure or the natural behavior. If I now say the particular, or the response due to a forcing function, now what's y sub p? Actually, and I'm not looking for the complete response. Now I'm just looking for the particular solution. And I've hit your system with this exponentially damped cosine. What are you going to see after your transients have disappeared? Or really, what's the structure of the particular solution? Is that clear what I'm asking? So don't worry about transients. I just want to know what's the particular structure. It's going to look exactly like the forcing function, isn't it? Except now it could be shifted, so I have the cosine and the sine piece. Meaning now y sub p of n is beta 1, 0.7 to the n cosine of pi over 8n plus beta 2 and you could find the beta 1 and the beta 2 by plugging in your forcing function and solving in that difference equation for the resulting coefficients. And your complete solution is made up of, structurally, of those two. So that now you would have an alpha 1, maybe these aren't the same alphas, but you could have written this down immediately once you found the structure of your input and you knew the poles of your system. This, boom, immediately jumps out at us. How are we doing? Is that okay? Let me give you another one. I'm having too much fun. Suppose you're given a pole zero diagram for some transform, capital X of z, what is the structure of little x of n? So that now suppose somebody gives you There's one. Let's say that we have two poles here, a pole here, a 0 here, and a 0 there. That's our pole 0 diagram, and this is 0.75 plus j 0.25. This is 0.5, this is 0.25, and the other one's at the origin. Can you give me capital X of z? Can you give it to me exactly? Is there any uncertainty in capital X of z? Or is there any variable in capital X of z? Pardon? I didn't give you a constant, did I? So you can tell me what factors are there. You have 2 zero factors and you have 3 pole factors. You can give me those, but I didn't give you the gain. So I know capital X of z to a multiplication factor or to a gain. I could now say capital X of z is alpha z, z minus 0.25. I have one pole that's real, and then I have a complex pole pair, which I can write as z minus the real part squared plus the imaginary part squared. If you look at the roots of that, that gives you these complex roots. I could give you that, or you could write that down immediately. And now that you know that, can you tell me what the structure of little x of n is? The structure, I'm saying you don't need to know what alpha is because I'm allowing you to just give me generic coefficients. Can you at least give me part of little x of n? What do you know? You know your poles determine your modes, right? And you know the poles. The issue now is, wait a minute, has he given us complex poles before? And I have, just indirectly. I've given those to you as exponentially damped sines and cosines. And that's really what this is representing. This is representing sines and cosines. What's their damped frequency of oscillation? Well, it's going to be basically it's the angle associated with that complex number. How fast does it collapse or how quickly does it grow? That's the magnitude of that complex number. Meaning if I wrote this not in rectangular form but in polar form, I now have 0.7902 at an angle of 18.43 degrees. I'm writing it in degrees just because it's easier than radians to visualize. So something a little less than 20 degrees. Now I know that x of n is, let's say, alpha 1, 1/2. That was one of my poles, wasn't it? And now I have the other pieces. I don't know how much I have of the cosine or the sine. They both could be there, so I'm just going to include them. But I now know that they decay with 0.709. That's my radius. That's how they collapse. Let me say this is now the cosine, and you would have to convert this to a radian measure and scale it by n in order to take the cosine, unless you're doing it with your calculator and your calculator's in degrees. And then we have our sine. That's now the structure of our little n. quick and dirty. But we found that from our complex polls. Question?
How do we determine n is greater than or equal to 0? How do we use conversion?
In this particular case, it's basically where are we assigning our origin in time. And so I didn't really tell you the region of convergence, but I sort of implied earlier that if it's not explicitly stated, we will probably assume that it corresponds to a causal waveform, which means that it's lying exterior to all of our poles. So I would have had to tell you where the region of convergence really was if this is a waveform, which I said it was, essentially, but now I just sort of said, let's agree if nothing is told. Or you could, on the exam, say, I'm assuming a causal waveform. And then you can say n greater than or equal to 0. I have a few more, but I'll just say that's probably good, okay? You've been very cooperative. I think I'm getting more reverberation because I have fewer of you in the room. You're offering less damping now than what was offered before. So I will see you Wednesday. I do have office hours. If you can't make those office hours, send me an email if you have last-minute questions, or maybe we can try to figure out how to connect. Okay? Good luck. Do effective studying, and I'll see you Wednesday at 5:30 for the exam.